Hello and welcome to this presentation related to compound angle formulae. This is a continuing presentation related to the combining of waveforms. So essentially in this presentation we'll be given two waveforms, one shown here and one shown here, both having the same angular frequency. We'll essentially summate them to form this resultant waveform shown here. Please note there are two previous presentations. The first one here is an introduction related to compound angle formulae. Here we introduce compound angle formulae and the various formats and solve various problems using these formulae. And the second presentation is essentially the precursor to this presentation, where we introduce the concept of combining waveforms that have the same angular frequency. It is strongly encouraged that you've reviewed these previous presentations before reviewing the contents of this presentation, as they contain underpinning knowledge of this topic area. So here's a few recap slides from these presentations. This slide here shows you the sine and cos formulae, labelled 1 and 2 here for reference, and show how they can be expanded into these forms here, 1a through to 2b. This slide recaps the basic sine wave, y is equal to sine x, plotted between 0 and 360 degrees, and also between 0 and 2 pi radians. Again, we've reviewed radians in a previous presentation. Here's a recap of the cosine waveform, y is equal to cos x, again plotted between 0 and 360 degrees, and 0 to 2 pi radians. Here's a recap slide of some basic trigonometric ratios, often quite convenient for us to refer to, related to the angles of 0, 30, 45, 60 and 90 degrees, in some cases shown in both surd form and decimal form. And of course we can determine these on the scientific calculator. So in this presentation I'm just going to work through one example, that's example 3 extracted from my notes, where we'll combine two waveforms using firstly a graphical technique and secondly an analytical technique. So part 1 of example 3, we're asked to use a graphical technique and plotting between time t is equal to 0 and t is equal to 0.1 seconds. We've got to determine the single wave resulting from a combination of the two waveforms shown here. That's the negative 20 multiplied by the sine of 30 pi t plus pi divided by 2. And we're adding to that 45 multiplied by the cos of 30 pi t minus 2 pi divided by 3. And part 2 of exercise 3, we've got to verify the graphical result obtained in part 1, but this time using a trigonometrical technique. This is our analytical technique, and that's where we're going to use compound angle formulae. So I'll now very briefly take you through the full work solution for example 3. Just for reference, if you want to jump straight to part 2 solution, the analytical solution, that commences approximately 6.5 minutes into this presentation. So this is example 3, part 1, the graphical method, commencement of the solution. So in the left hand column here we have the time t between 0 and 0.1 seconds, as stated in the question. And I've simply used a spreadsheet here to determine the values for the waveform negative 20 multiplied by the sine of 30 pi t plus pi upon 2. So when t is equal to 0, the answer is negative 20. When t is equal to 0.005, the answer for this waveform is negative 17.8201. 4 decimal places, and so it goes on. We do exactly the same for the second waveform, 45 multiplied by the cos of 30 pi t minus 2 pi divided by 3. So when t is equal to 0, here's the value. When t is equal to 0.005, here's the value, and again, so it continues. And the right-hand column is simply a summation of these two waveforms. So negative 20 added to negative 22.5 is negative 42.5. And again, so it goes on. So this is the graphical method. And I said essentially I've used a spreadsheet here Example 3, the graphical solution continued. So I'm simply now plotting on the diagram the various waveforms. This is the first waveform shown here, the dashed line. The second waveform shown here, the longer dashed waveform shown here. At any particular point between 0 and 0.1 seconds, I simply add the height of the yellow waveform, the first waveform, to the height of the second waveform. So essentially adding the red height for the first waveform to the green height here for the second waveform allows us to find the height of the resultant waveform at this particular position, shown here. This shows the amplitude of the yellow waveform added to the amplitude of the green waveform, thus showing the resultant waveform when t is equal to 0.03. So applying this approach to various points between our plotted range, we now plot the resultant waveform, shown here. So in essence, the yellow waveform added to the green waveform has produced the purple waveform. So that's the solution to example 3, part 1, using our graphical technique to combine two waveforms having the same angular frequency into one resultant waveform. Example 3, solution continued. This is now part 2 of the solution, where we're going to combine the waveforms, this time using an analytical method. In other words, using compound angle formulae. So here are the two waveforms we've been given. Here's our first waveform and our second waveform. We've got to express both of these in the form of one single waveform having the form of r multiplied by the sine of omega t plus or minus alpha. Just note for reference, of course, that the omega values for these two waveforms on the left hand side are both 30 pi. So considering the first waveform, the negative 20 sine of our bracket waveform shown here, so this part of the waveform has the form sine a plus b, where a in this case would be 30 pi t, shown here, and b would be pi upon 2, shown here. So from our compound angle formulae, this listing here, we can see we require formula 1a as labelled here. So this is our formula 1a. And we just insert our a value and our b value into the formula. Notice the compound angle formula is in a bracket because we're multiplying the whole bracket by the negative 20, shown here. Evaluating cos of pi upon 2, that becomes 0, cos of 90 degrees is 0, and sine of pi upon 2, sine of 90 degrees is 1. So from our recap slide here of the cosine waveform, at pi upon 2 or 90 degrees, the ratio on the vertical axis is 0. And from our sine wave recap slide, at pi upon 2 on the horizontal axis, 90 degrees, we can see that the sine ratio is 1. That's where these values have been extracted from. The rest is evaluation. Notice I'm using radians here throughout because my angles are in radians. We can replace the negative 20 sine of 30 pi t plus pi upon 2 with negative 20 cos of 30 pi t. Example 3, solution continued. Now we adopt a similar process for the second of the waveforms we're given. So from our compound angle formulae listing this time, you can see we have the form cos of a minus b, shown here, and expanded here on the right hand side. Again, back to our original listing from our previous presentation, we can see that the formula we're using here is labelled 2b, cos of the difference of two angles. Difference of two angles A minus B. So in this case, our angle A is 30 pi t, and our angle B is 2 pi divided by 3. We adopt exactly the same process as before, inserting angle A into the formula inserting angle B, and again evaluating. Just note that cos of 2 pi upon 3 is negative 0.5. Note that 2/3 of pi is 120 degrees. That's how we read off the negative 0.5 on the vertical axis for the ratio. And on our sine wave, here's 2/3 upon pi, 120 degrees. And the ratio is, in decimals, 0.866. Or in third form, that's 0.5 multiplied by the square root of 3. Just note, if you don't want to use the third form, you can use 0.866, which is the sine of 2 pi upon 3, stated to 3 decimal places there. Again, notice the compound angle formula on the right hand side is all in a bracket, and the 45 factor is outside of the bracket. So from this expansion, 45 cos of 30 pi t minus 2 pi upon 3 can be written as negative 22.5 multiplied by the cos of 30 pi t plus 22.5 multiplied by the square root of 3 multiplied by the sine of 30 pi t. All I do now is state the original two waveforms that we're trying to combine, that were given in the question, and I replace them with their equivalent from our compound angle formulae. Notice the like terms here, summating produces this term here. Example 3, solution continued. On this slide, I'm simply checking out the original waveforms with the now combined waveform on the right hand side to make sure numerically they're correct. So this is just to spot checks at particular values of t. So all I'm doing here is choosing a value of t is equal to 0.03 seconds, and I'm inserting this value wherever there is a t in the above equation. Evaluating, I find that the left hand side is 52.463, the right hand side 52.463 to 3 decimal places. And referring back to part 1, our graphical method for time t is equal to 0.03 seconds. The combined waveform has a value of 52.4626 to 4 decimal places. So that confirms our answer to 3 decimal places. And just another spot check when t is equal to 0.1 seconds. Again, inserting the 0.1. I evaluate left hand side and right hand side are equal, 42.5 in this case. And again, referring back to part 1, the graphical method, for a time of 0.1 seconds, the combined waveform value is 42.5. So that suggests that the equation shown above is correct using our compound angle formulae. Again, visually you can see here for 0.03 on the horizontal axis, we appear to be in the region of 52, 53 on the vertical axis, and for the t value of 0.1, again, we appear to be in the region of 42, 43 on the vertical axis. So it appears that our equation that we formed, top of the slide here, is correct. Example 3, solution continued. So now we've expressed our originally 2 given waveforms into this format shown here. We can now place them into the r sine omega t plus or minus alpha format, which the example requires us to do. Just noticing copying the right hand side of the top equation to here, I've just calculated the 22.5 multiplied by the square root of 3 as to be approximately 39. I'm just doing that for convenience of the calculations. We will induce a slight inaccuracy, but I think it's simpler for the presentation to use 39 instead of this value here. So again, we're going to refer to our list of compound angle formulae, and r sine omega t plus alpha can be expanded into this form shown here. And again, referring to our slide, list all the compound angle formulae we're considering. We're going to use formula labelled 1a here. The sine of A plus B expansion here. So noting that in this case the angle A is omega t, shown here and here. Angle B is alpha, shown here and here. We're going to use the same technique we used in the previous presentation to first of all find the resultant of our two waveforms when combined, and also the phase angle. This line here, I've simply rearranged the right hand side so that I can equate my coefficients. So equating coefficients of the sine omega t terms, I would equate the 39 with the r cos alpha, that's shown here. I form an expression for cos alpha. And equating coefficients of the cos omega t terms, I will equate negative 42.5 with our sine alpha, and that's shown here. Again, I can rearrange this time for sine of alpha. As using the method termed equating coefficients, initially of sine omega t, and secondly equating coefficients of cos omega t. Example 3, solution continued. Now noting from the previous slide, we have a negative sine ratio here and a positive cos ratio from figure 2 of our notes, shown here in the ASTC diagram. A positive cos and a negative sine ratio occurs in what is termed the fourth quadrant. So our phasor will be at some orientation here, where alpha will be negative, measured in this sense. So now to find the value of r, we're going to use Pythagoras' theorem. In this case it's 39 squared added to the 42.5 squared, or square rooted. Notice I've ignored the negative on the 42.5 because I'm squaring the value anyway. So that produces the value of r, stated here to 4 decimal places. And from our trigonometric ratio, to find angle alpha, I'm actually going to measure angle alpha negative, so it's actually this angle phi labelled here. That's simply the inverse tan, or the arctan, of negative 42.5 divided by the 39. So alpha is actually negative this time. Its sense is opposite to that shown here on our diagram. It's negative 47.4590, 4 decimal places, and I've also converted it in terms of radians here, negative 0.8283. Again, 4 decimal places. So finally we have our resultant waveform in the form of r sine omega t plus or minus alpha. In this case it's 57.6823 multiplied by the sine of 30 pi t minus 0.8283. Slight rounding there because I've used 39 instead of 0.5 multiplied by the square root of 3. Example 3, solution continued. I'm now going to try and verify the expression we derived on the previous slide, repeated here for convenience, by choosing a few arbitrary values of t. So for example, when t is equal to 0.05 seconds, simply insert the value of t into the expression, and that produces an answer of negative 39 to 1 decimal place. If we review the graph shown here below of the resultant waveform, that's the solid line on our graph as before, we can see that for value of t of 0.05 here, we have something in the region of negative 40, so negative 39 would seem reasonable from our calculation. And if we take another value of t, say 0.09 seconds, again insert that into our expression here, that evaluates to 56.5 to 1 decimal place. And again from our graph, in 0.09 seconds, we can see that on the vertical axis, a value in the region of 56, 57 is determined. So again, the expression seems to be quite accurate. Remember, of course, the resultant waveform is the resultant of adding these two waveforms we were given in the original problem. And again, returning to part 1, the graphical method, these are the tabulated values. If we scroll down to t is equal to 0.05, we can see we have negative 38.9711, and our answer is negative 39 to 1 decimal place. That seems reasonable. And if we scroll down to the t is equal to 0.09, we have a value of 56.5092 for the resultant waveform. So 56.5 to 1 decimal place again seems reasonable. So we now have the final expression for the combined waveform required with example 3. And just for reference, this slide relates to the determining of angles alpha, predominantly specified in radians, and the phasors are in different quadrants of our ASTC diagram. Phasors here are represented by the red lines of length r. When the phasor is in the first quadrant, the components of the phasor are both positive, but when the phasor is in the second quadrant, shown here, notice the x component of the phasor is negative and the y component is positive. When the phasor is now in the third quadrant, shown here, both the x component and the y component of the phasor are negative. And when the phasor is shown in the fourth quadrant, shown here, the x component is positive, but the y component is negative. Note also that angle alpha can be measured positive in an anti-clockwise direction from axis OX, shown here on this diagram, or it can be measured negative in a clockwise direction from axis OX, shown here. So do be aware of the orientation of the phasor, because often students will calculate the magnitude correctly, but they will state angle alpha incorrectly. Alpha is always measured from the OX axis, shown here. I would encourage you to stop the presentation and review this slide at your own pace so you fully understand the various orientations of the phasors and how to calculate the respective angle alpha. I will leave you with some tutorial questions to attempt at your own pace. Again, we have to use both the graphical and the analytical method in the solutions. Here's question 1, question 2, answers shown in the square brackets. And question 3, again answers shown in the square bracket. Hope this presentation has been of some use to you, and thank you for viewing.